Glaciers and glacial processes. In this lecture, we will investigate the types of glaciers, how glaciers form in different climates, cold ice versus warm ice and how pressure can change the melting temperature of ice, and the processes by which glaciers move. A glacier is a large, thickened mass of ice that forms when snow remains in one place long enough to transform into ice. Although apparently solid, glaciers flow like rivers and are capable of extensive landscape modification as they move. Glacial ice covers approximately 10% of the Earth's surface and locks up almost 80% of the planet's fresh water. The frozen water of the world is known as the cryosphere and encompasses sea and lake ice, snow cover, ice caps, ice sheets and glaciers, and frozen ground such as permafrost. During the Pleistocene Ice Age, approximately 32% of the total land area of the planet was covered in glaciers, including most of Canada and all of southern Ontario. The landscape we see around us today is the result of glacial advance, retreat, and deglaciation over the last 2.6 million years. Since the end of the last ice age, most of Canada's glaciers have disappeared, leaving only about 2% of the country still under ice. Most of these are relics of the late Pleistocene Ice Age. However, during the late 17th century to the late 19th century, the planet experienced a little ice age when global temperatures were consistently low enough for glaciers to advance. Most glaciers in Canada are found on the Pacific coast and flow from the large ice field in the Yukon and British Columbia, which covers over 29,000 kilometers square, or on the eastern Arctic islands, where Nunataks, Cirque, and Valley glaciers extend over 145,000 square kilometers. Glaciers are classified according to their temperature, morphology, and geographic location. Large continental to subcontinental ice sheets, ice caps, and ice shelves form at high latitudes and only occur in Antarctica and Greenland. Smaller glaciers, often fed by ice or snowfields, form at high altitudes in Alpine regions. This table, taken from Trenhale, describes some of the more common types of glaciers. Ice sheets and ice shelves are only found in Antarctica and Greenland and are likely remnants of the Pleistocene continental glaciation that ended approximately 10,000 years ago. Ice caps are smaller features, but again are only found in polar or subpolar regions. The remainder reflect alpine glaciation and are found in temperate latitudes at high altitudes in mountainous regions such as the European Alps, high Andes, and the mountain ranges of northwestern North America, including British Columbia, Yukon, and Alaska. Antarctica and Greenland host the only subcontinental to continental scale ice sheets remaining on Earth. Ice sheets cover areas greater than 50,000 kilometers squared and form large, dome-shaped bodies of ice. Ice sheets develop in areas of low relief, but are often very thick. Ice sheets grow radially outwards in all directions. Antarctica's ice sheets began forming around 30 million years ago and are remnants of the last ice age. Ice shelves surround Antarctica, where the ice sheet has extended over the ocean and floats on the water. 98% of the Antarctic landmass is covered in ice, which contains about 90% of the world's ice. In Greenland, the ice is greater than 30 kilometers thick in places. In the center of the ice sheet, the weight of the ice has depressed the bedrock below sea level in a phenomenon known as isostatic depression. If the glacier melted, the bedrock would return to its original elevation. Ice caps are smaller than ice sheets, covering less than 50,000 square kilometers, but have a similar dome-shaped morphology. Like ice sheets, they form in areas of low relief, but typically at higher altitudes and in Arctic to subarctic regions. The Vatnajökull ice cap, shown here on the eastern part of Iceland, is a classic example. Alpine glaciers are the classic glaciers we see in European mountain scenes. Alpine, or valley glaciers, are streams of flowing ice confined to steep-walled valleys in mountain settings. They are fed from ice or snowfields, cirque glaciers, or outlet glaciers. These glacial features are much smaller than the continental scale ice that forms at the poles. This is an example of a cirque glacier in the Mont Blanc Massif in France. Cirque glaciers occupy bowl-shaped depressions in mountains and feed into valley glaciers. Valley glaciers are rivers of ice that carve their way through steep-sided valleys. This image shows Bear Glacier, located in British Columbia's Coast Mountains. The glacier once filled the valley, but has been retreating since the 1940s. Piedmont glaciers are lobe or fan-shaped glaciers that flow out onto glacial outwash plains without reaching water. This image, taken in 1994, shows the Malaspina Glacier in the St. Elias National Park in Alaska. This false-colored aster image of the Malaspina Glacier, taken in 2001, shows significant ice retreat. In this image, snow and ice appear light blue, dense vegetation is yellow, orange, and green, and less vegetated, gravelly areas are in orange. According to geologists, the glacier is thinning and retreating, and only the fact that the ice is protected from the ocean by its terminal moraine is preventing a more rapid retreat. Hanging glaciers sit high on valley walls and transfer material by avalanching and ice falls. This image shows the Cook Glacier on South Georgia Island. 20 years prior to this photograph being taken, the glacier would have completely covered the foreground. Glaciers form in areas of high precipitation and low temperature, where snow falling from year to year has the opportunity to accumulate rather than melt. Each year, new snowfall buries and compresses the previous year's layers, much like sediments accumulate to eventually form sedimentary rocks. Snow accumulates through snowfall, condensation and freezing, and transportation by avalanches. Initially, the snow contains about 90% air, but as more and more layers accumulate, the snow begins to recrystallize under pressure to form firn, granular ice comprising about 30% void space that is transitional between snow and glacial ice. In a process that may take years to thousands of years, depending on climatic conditions, glacial ice forms. Eventually, glacial ice becomes so dense it contains almost no air bubbles and appears blue. The ice itself is impermeable to water and has a density of around 900 kilograms per cubic meter. Active glaciers have two main components, an accumulation zone and an ablation zone, separated by the equilibrium line. In the accumulation zone, more snow and ice accumulate in the winter than is lost in summer, resulting in a net increase in both. In the ablation zone, snow and ice are lost in the summer at a faster rate than they can accumulate in the winter, resulting in a net loss of material. Accumulation is mostly the result of snowfall, although additional accumulation may be due to rainfall freezing on the surface, condensation and refreezing of meltwater and slush, and avalanching. Coastal areas have the highest rates of accumulation. Ice loss, or ablation, occurs mainly through melting. It can also occur due to evaporation, wind and river erosion, sublimation, and calving into lakes or the sea. Calving is a relatively rapid process whereby large chunks of ice fall off the front of the glacier, and it usually results in steep ice cliffs and produces icebergs. The equilibrium line is the point when neither process dominates. Snowfall equals snow melt. When net loss is greater than net gain, glaciers will retreat. If overall accumulation exceeds ablation, the glacier will advance. Glaciers that have a positive mass balance, that is, accumulation exceeds ablation, are advancing. Advancing glaciers typically have steep vertical fronts, such as that seen in this image of the Franz Josef Glacier in New Zealand's Southern Alps. Most of the world's glaciers are retreating. As a result of the warming climate, snow and ice do not have an opportunity to accumulate, resulting in a negative net mass balance. This image, which shows the Athabasca Glacier in Canada's Rocky Mountains, shows the characteristic debris-covered, gently sloping snout of retreating glaciers. The Athabasca Glacier has retreated about 1.5 kilometers in the last 125 years. Glaciers are classified according to their temperature or thermal regime into warm ice and cold ice. Thermal regime is important as it determines how a glacier moves and how it erodes, transports, and deposits material. Glacier temperature depends on a number of factors, including the amount of solar radiation the ice receives, the air and snow temperature, and how much latent heat is released during refreezing, from geothermal sources, and from friction. The classification of glaciers into warm ice or cold ice depends on whether the ice is near or well below the pressure melting point of ice. The melting point of ice decreases with increasing pressure. Therefore, water stays liquid at colder temperatures underneath a glacier due to the hydrostatic or cryostatic pressure of the ice above it. Warm ice contains water throughout and typically associated with mid-latitude alpine glaciers. The presence of water allows for sliding and facilitates debris removal. Cold ice does not contain liquid water and is frozen to the bed. In temperate or warm-based glaciers, the temperature at the base of the ice is warmer than the pressure melting point, meaning that there will be liquid water at the base of the glacier. Water also accumulates on the surface during the summer, and this water may end up at the base via glaciofluvial processes, adding to the volume of water between the ice and the bed. Water lubricates the bed and facilitates movement due to basal sliding, which may occur quite rapidly. In polar cold ice glaciers, surface temperatures are too cold at any time of the year to facilitate melting. Further, the temperature at the base is well below the pressure melting point, meaning there is no liquid water between the ice and the bed, precluding the possibility of basal sliding. Cold ice glaciers only move via internal flow, either brittle or plastic deformation, and so move extremely slowly. Glaciers move, flow, and deform in response to gravity. Ice flows in general, from high altitude to low altitude, and high latitude to low latitude, although there may be local perturbations. Glacial advance stops when melting or ablation equals accumulation. Glacial retreat, which is measured by the location of the snout or the terminus, is a function of melting or ablation, and not by backwards flow. Retreating glaciers are still moving forwards. Active glaciers transport snow and ice out of the accumulation zone and into the ablation zone. Warm, wet glaciers with steep mass balance gradients in temperate locations can move at rates between 10 and 300 meters per year, although rapid movement is uncommon. Cold, dry glaciers in polar locations move extremely slowly. A glacier's snout can advance, retreat, or remain stationary, but as long as there is an accumulation zone, the glacier will be active and flow. It is important to remember that an active glacier is always moving forward, even if it is in retreat. Glaciers do not retreat by moving backwards. Glaciers move fastest near the equilibrium line and away from the margins and bed where friction is greatest. Scientists have come to realize that there are a number of mechanisms by which glaciers can move. Basal slip, which is movement along the bed of the glacier facilitated by a thin layer of water, is perhaps the way most people expect glaciers to move. However, its efficacy as a movement mechanism is dictated by factors such as bed slope, ice thickness, ice temperature, whether it is a warm or cold ice glacier, and the underlying substrate. Highly fractured bedrock, for example, will not facilitate basal slip, as its high permeability allows water below the glacier to drain, rather than forming a thin layer at the base of the ice. Unconsolidated sediments will behave similarly. Other movement mechanisms include plastic flow, movement by fracturing, bed deformation in unconsolidated sediments, and ice regelation. In the top 50 meters of a glacier, ice behaves as a brittle solid and moves by fracturing, leading to the formation of crevasses. The Risting Glacier on South Georgia Island clearly illustrates the upper fractured layer. Plastic deformation is the result of deformation of ice crystals at the atomic scale, the sum of which leads to glacial movement. It is the dominant form of movement where there is sufficient pressure, i.e. below 50 meters. In the lower parts of the glacier, the pressure is sufficient that the ice behaves pseudoplastically, creeping or flowing under its own weight. Plastic deformation takes place either by slipping along shear planes within the crystal lattice or by recrystallization. In areas where glaciers are underlain by unconsolidated sediments or weak bedrock, movement can take place as a result of bed deformation. In these situations, the sediments move and deform, carrying the glacier down slope. Subglacial water is a factor in bed deformation, but unlike basal slip, the water does not lubricate the surface, facilitating movement. Instead, increasing pore pressure in the sediments decreases the soil strength, increasing the strain rate in response to the stress of the overlying ice. Evidence for bed deformation includes features oriented parallel to the direction of ice movement, such as drumlins. Regelation is the process of pressure melting, whereby ice under pressure has a lower melting temperature than unpressurized ice. When glaciers moving downslope encounter obstructions, increased pressure at the obstruction leads to melting. Liquid water flows over the barrier and refreezes in the lower pressure zone downslope of the obstruction, releasing latent heat. This process facilitates ice movement at the base of the glacier. Glaciers are accumulations of ice and snow that move and flow like rivers of ice. The very large continental scale glaciers only form in polar or subpolar locations, whereas mountain glaciers can be found worldwide in temperate alpine regions. A glacier's thermal regime, whether it is warm ice or cold ice, dictates its movement potential, and movement of glaciers proceeds by a number of complex processes. As agents of change, glaciers are particularly effective. Moving glaciers exert huge forces on the landscape, carving, scouring, eroding, transporting, and depositing material as they move. Southern Ontario's landscape has been drastically altered by glaciation during the last 2.6 million years, and the landscape we live and thrive in today is a direct consequence of glacial action on the continent. In the next lecture, we'll look at glacial landforms and the processes by which they were formed.